My general field of study is solar physics, and my specific areas, a few different areas of study. So as a graduate student, I was studying the connections between solar flares and coronal mass ejections. I was also involved in a hardware project where I was actually contributing some of the software, but it was an instrument built at the Royal Observatory Belgium called Proba2, and I was responsible for calibrating the temperature response of the instrument. So we were looking at how the atomic physics models resulted in temperature dependence, so we could tell the different temperature of plasmas that we were looking at. So that was very interesting. And then after I moved to UC Berkeley, where I was a postdoc, I started to work on a project that it was using artifacts out of the Solar Dynamics Observatory AIA instrument, the Atmospheric Imaging Assembly instrument, and I that was one of my favorite projects to do so far, because it was using the phrase "one man's trash is another man's treasure." In this case, that was kind of true. So the data that AIA was collecting, it's an image. It's a very high resolution imager that collects data at different wavelengths and therefore different temperatures of emission coming from the sun. But when we get a solar flare, the intensity of the little tiny flare region gets really, really high, and that saturates cameras. And normally what happens is you get bleeding, so pixels, they reach capacity, and so their electrons start to spill into neighbouring pixels, so you get this bleeding effect, like a star shape. But because of the way the camera was built, and this was work that I started as a graduate student working on Proba2, the way the filters are set up, they're very, very fine filters, they're thin films, and because they're so fine, they're on the front end of the camera, and they have to prop them up using a mesh grid, and so they basically have a mesh like you'd see on a window or something like that, and then the film sits onto this, and that mesh inadvertently acts as a diffraction grating. And so what ends up happening is when you get this bleeding pattern occur, you get diffraction patterns forming. So you're able to see this in multiple different instruments, but it was particularly interesting in AIA because there was actually two meshes they deliberately offset them, expecting this to happen. And it meant that we were able to use those diffraction patterns to get at the true intensity of the flare pixels, which was the first time that really had ever been done with any kind of regularity, mostly because it gets so hot and so bright that you can't see any detail. And so we were able to take those diffracted pixels and put them back into their original spot and figure out just how bright and therefore how hot the kernels of the solar flares were, which was that was pretty cool, because it all revolved around some very straightforward physics. It was very, very detailed work, but I really enjoyed that project. I was hired to come to UC Berkeley as a postdoc to be a part of the RESI satellite team. A large part of my responsibilities for RESI was being what they call a towban, which is sort of like a babysitter for the mission, which is much more than being a babysitter oftentimes. So the satellite is in orbit, and we have opportunities to talk to it every 90 minutes or so for about half the day, or about a third of the day. And during that time we need to send it commands if we want it to change what it's doing or receive data. And it has a solid state recorder, so basically a videotape on board, and that videotape is only so long, and once it gets to the end of the videotape it just starts to overwrite itself. And so a large part of the role of the towban is to make sure that it's not taking so much data that it just overwrites its own data, and we have to make sure that we dump it back to Earth sufficiently frequently so as we can try and keep as much of that as possible. So that's kind of a delicate balance, and there's a number of dials that you can tweak on that. So I worked very closely with the Mission Operations Centre here. As part of the science team, you know, I was part of the decision-making process on what we would do, and then we would work with the operations team and they would actually implement the changes that we would like to make. So that was a very different type of position, or type of role than I'd had before, but it was very interesting. I learned a huge amount during that time. I was analysing RESI data as well, so to tie back to the diffraction pattern project, the other side of that was we were using RESI spectra imaging spectroscopy to work out the energies that were being dumped into the solar flare kernels, and so tying the two of those together, we were able to tell a lot more about the physics that were going on in solar flares. So that was I worked very closely with some of the experts on the team who knew really the ins and outs of that. I did some of that myself as well, but I mostly partnered with other people on the team, collaborated with them, and we worked together on those.